Hello, and welcome back to Engineering 201 Electrical Fundamentals. And I think the last lecture we had talked about capacitors, and I wanted to continue on and talk about then inductors. When we think about energy storage elements, there are two of them, capacitors and inductors, and hopefully we've got a better understanding of capacitors, so it's now time to do the same with inductors. If you think about an inductor, what an inductor is it's essentially a coil. So you could take a wire and wrap it around some core. The core might be an iron core. It could be air. If you just take a coil of wire and have it in the air, then your core is going to be air. And we'll talk about how that can affect things. So we've taken this wire and we've wrapped this wire around this core here, and because of this current going through that, there will be a magnetic flux coming off of this. And very quickly we're going to try and put this whole thing into a box so that we can look at just terminal effects. We'll look at this like this, and talk about if we have some voltage across here, maybe V of t, this is usually time varying, and have some current here, I of t. We can talk about the relationship of this. This is given then as the inductance is L. And we can say that L is defined as inductance, which we give the unit of henries. Named after Joseph Henry, the American physicist. Henry's, which the base unit on that would be what, a volt times a second divided by an amp. And if we look at the governing equation, what we get out of this thing, the governing equation, is that the voltage is equal to the inductance L times the time rate of change of the current. Okay. So V is equal to L di dt. We'll see a lot of similarities and differences. If we were in an English class, we'd talk about comparing and contrasting the inductors and capacitors. Remember, with the capacitor, you had that I was equal to C times dV dt. Here we have V is equal to L times di dt. One of the things maybe we should talk about is where we find these things. So lots of places that you can find them in terms of electronics, filters, and things like that. And we'll talk more about those next term. Maybe to try and think of some things where you might not necessarily think of them right off the bat. This is for our civil engineering friends. Let's say that we have an intersection here in a highway. And you've probably, no doubt, seen these circles cut in the pavement here. Make sure I get these on the correct side so we're not driving. There's some circles there, and what those are is those are coils. They usually have wires that go off to the side, and then there's some control box over here. Wires going off to the side there, wires going off to the side there. And this is the hallmark of a traffic-controlled intersection. That these coils, when you think about this coil here, like this, when there's no car there, the core is going to be asphalt and air. This is embedded in the asphalt. And when you have then a car drive over this thing, like this, the core is now asphalt, air, and car, or iron. Car's probably got some iron in it. So we've got some iron, so the inductance changes. So what this is doing over here is just really querying what the inductance is. So that you can figure out where the car is. This is a very effective way of doing this because it doesn't have to deal, if you try to do it with an optical sensor and it snowed or something like that, it would probably be not very reliable. But when we have this, it's really quite reliable, and that's how they do traffic control. And you'll see these located. You can even see small ones in bike lanes and sometimes they'll be back quite some distance so they can get some idea of how many cars are in there, so that the light is only on long enough just to let the required number of cars through and then switches to the other lane. Done right, these are very effective intersections. So this is something where our civil engineers will use this to their advantage. Another one is an inductive pickup, a little bit like how a tape recorder reads a tape, or used to read a tape. I don't know how many people are using that technology anymore, but if you have a toothed wheel like this, I don't think you want to watch me draw all the teeth here. So let's say that this is rotating. What we do is we put the coil right here, and we query the inductance, and as this tooth comes around, it's going to change the inductance of that. So a lot of times if you have a crank position sensor or a tachometer or something like that in your automobile, it's probably using this type of technology. If you've got a spark ignition system, it's probably using this kind of technology to figure out where that engine's at and the timing of things in it. Another place that we use inductors a lot, and we're going to really, and maybe I'll separate that from this, we'll talk about it a lot more next term, is mutual inductance, where we take two of these and we wrap them around the same core. Might take something like this, and we get a transformer out of that. And we use that to, of course, step voltage down or step voltage way up, depending on which way you use it. This thing works both ways. It'll work this way and it'll work that way. So if you want to step the voltage up, you can use it one way. If you want to step the voltage down, you can use it the other way. There's a corresponding increase or decrease in the current, so you're not changing the power. You're just stepping voltage up and current down, or vice versa. And we actually use this in the automotive system. For basically this transformer is what you have with a coil when you want to have very large voltages in a ignition. You're going to need 40, 50,000 volts to fire that spark plug. You'd have something like this, and the points would just be opening and closing it, so you wouldn't have a constant current. So we'll talk about a lot of this on its own next term, but there's a lot of use for inductors. So let's look a little bit at this equation here. We can say that this looks like a short to a DC. Okay, so it looks like a short circuit to a DC. I always say inductor looks like a heater to a DC circuit. And you might say, well, you were just saying that they use transformers in automobiles. How does that work? Isn't it a DC system? Well, yes and no. It's a DC system, but when the points, or however you're turning this on and off, it's a DC system that looks like this. It's on, and then it's off, and then it's on, and it's off. So it is actually a changing current. The other thing is we cannot have an instantaneous change in current. Okay, cannot have an instantaneous change in current, because if you try and have an instantaneous change in current, you're going to need an infinite amount of voltage, right? Di dt, that would force the V to be 0. I mean, I'm sorry, not V equal V 0, but the voltage, that would force it to be infinity, which you couldn't do. Now, as a student, I always didn't like things like this because I thought you could probably have an instantaneous change in current. I mean, if we take this thing and we cut through this, you cut through that with a fire axe or something like that, that would seem fairly instantaneous to me. But that's probably a good example and a good thing to talk about. If you've ever taken an appliance that's predominantly inductive, like a motor or something like that, and you unplug it, you'll probably notice a fairly large spark. And that spark is actually the magnetic field collapsing. So again, with the capacitor, we had an electric field. With the inductor, we have a magnetic field. Okay, we have a magnetic field, and when you unplug something, which is probably not good because switches are designed to deal with that, plugs are not necessarily designed to deal with that. When you pull the plug on something like a motor, something that's predominantly inductive, and you see this large spark, that's what's bridging this gap. That's what's allowing it not to have an instantaneous change in current, and the magnetic field is collapsing. So a couple kind of interesting things and hopefully practical things. If let's see, what else can we learn here? If I is equal to a constant, then what? V is equal to 0. That goes back a little bit to, it looks like a short to a DC. Probably the most important thing to take away from this, other than, there's a schematic symbol, we want to try and draw it nice and neat because we don't want it to accidentally start looking like a resistor. That's kind of a liability. But that brings us into a good subject, because as we are wrapping this wire around this core, we're making inductance, but we're also making resistance. You can just wrap up wire and you'll make resistance. The longer the wire, the more resistance that you're going to have. So while we might say that this is an ideal inductor, if we look at a more real-life inductor, it looks like what? Well, there's going to be some inductive portion, and then I'll try and make good schematics there. So there's the inductor with the loops, and there's the resistor. We don't want the loops. So your inductor here, and it's going to have a lot of resistance. We'll sometimes call that R sub L. That's the internal resistance of the inductor. So the inductor, by virtue of its construction, will oftentimes have a very high internal resistance. That's why we don't necessarily have to worry so much about safety issues with inductors. You don't have to worry about them storing charge for a long period of time, because the internal resistance will usually dissipate that. So when we think about inductors, we may be thinking about this, but we maybe should think more about that it has some significant resistance along with it. Well, with that introduction and taking this and putting it into our model here, where we just look at terminal effects, you'll spend a lot more time in physics talking about, well, what if the core is changed from air to asphalt, or whatever the case that you had here? What if we add terms to this? What if we change the diameter of the core and things like that? You'll spend a lot of time talking about that in physics, but I want to take this and put it in to something where I just look at the terminal effects. You tell me what L is, what the inductance is, and we can then relate voltage, and we can relate current. And I want to do it by using the governing equation here. So with that, let's continue on. And I do very similar work to what I did with the capacitor. If I start out with our equation that the voltage is equal to L times di dt, and I'm using lowercase for both I and V because those are going to be time varying. I'm going to use uppercase L. Now you can have time varying inductance. Obviously here, well, in both of these cases we had changing inductance, didn't we? Or you can slip the core. If you move the core up and down in this, that's going to change the inductance. And sometimes when you adjust a welder, it feels like something heavy is moving in there, and that's exactly what's happening as you're moving the core inside the welder. So L can change with time, but we're gonna figure that it's constant. And if I then want to solve for the current, I can say that I, as a function of time, is equal to 1 over L times the integral from minus infinity to t of Vx dx. Don't change a variable there, because then x is equal to t and x is equal to minus infinity. I'll put a box around that. So I'm trying to take this one here and turn it into current. So I solve for the current, which is going to say that I of t is equal to, I can break up the integral, I can integrate this thing essentially 1 over L times the integral from minus infinity to t naught, which would be the initial current. I could say I T naught, and that's in an inductor very often equal to 0, plus 1 over L times the integral from x equals T naught to x equals T of V of x dx. So we could have something like that. So sometimes they'll just write it as the integral of V dt, if you will. So we've got voltage, we've got current. Now we need to look at power. Well, power, as a function of time, I'll use lowercase again, is the product, Watt's law, of voltage times current. So if I substitute those in, we're going to write everything in terms of current. Voltage, we said, was equal to L di of t times I of t. So that would be our expression for power is equal to L like that. Maybe I'd better separate that. So that would be our power expression. Of course, that would be in watts. And then energy. Let's look at energy. So looking at energy, I could say that I'll use the same variable, W sub L. We use W sub C for the capacitor, and I should probably make that time varying. So I'll use a lowercase. There we go. Is equal to the integral from minus infinity to t of the power, which is going to be the integral from minus infinity to t. Making a substitution for power, I have L di x dx I of x dx. When the smoke clears on that, just like it did with the capacitor, we have that the energy is equal to 1/2 times L times I of t squared. So this is energy. And I guess I should be clear here. This would be x equal and x equal. A lot of times people don't do that. They leave it as t. A couple different ways to do that. But this is what we really want to take away from it, these equations. This equation here for energy, and that's going to be joules. Okay. So just like with the capacitor, we have our expression for voltage, we have our expression for current, we have our expression for power, and we have our expression for energy. So just like with the capacitor, I'd like to tackle a problem. In some regards, this may be an easier problem. Some regards, it may be a more difficult problem. But let's say, and this will give us an idea of how these relationships for voltage and current and power work with each other. So let's say that I'm given something like this. We'll take a current source and run that through an inductor. We see already that's fairly theoretical. I haven't accounted for any resistance here, and sometimes that can be a big deal. And we would have some voltage across here, like this. And we're going to say that this is 100 millihenries, okay, which I'm not sure that I gave a very good description when we introduced the inductor. The units are henries, okay, and a henry is not as large a quantity as a farad. We do sometimes see a lot of milli or even micro henries, but it's much more common to see a 1 henry than it is a 1 farad device. So just to give you some warning there, we use a lot of millihenry inductors, but you can get up to 1, 2, maybe 10 henries, whereas a 10 farad capacitor is very, very uncommon. So this is our unit for our inductance, henries. So with that, I could talk about the current. I'm going to say that it's equal to 0 for t less than 0. And I'm going to say that the current is equal to 10t e to the minus 5t for t greater than 0. So if I were to graph this thing, the graph is going to look like this. I've got I of t and t in seconds. So when I graph this thing, we've got 0 up to here, and then you throw this in a computer algebra system or pick some points, however you want to do it. You're going to get something that comes up and then down like that. And this point here, if we were to look for the maximum, and I guess we could use our good old calculus on this, couldn't we? What if I were, because we're going to use this expression here, so if I say di dt of this thing, what's that going to be? Well, I have a constant times a product, don't I? So if I look at that, I could say that that's 10 times, now I need to use the product rule or the chain rule, which is going to be what? Minus 5 t e to the minus 5t. So I've taken t and I've multiplied it by the derivative of e to the minus 5t, and then I need to follow through the product or the chain rule, and I will have 1, that's the derivative of the t, times e to the minus 5t. So when we get done with the work on this, this turns out to be 10 e to the minus 5t times what? 1 minus 5? Minus 5t. Okay, so that's the derivative. And I guess we go back and look at our math. We figure out when this is a maximum. For maximum or minimum, if we got the shape of the graph, we know it's a maximum. For maximum, we will see that di dt needs to be equal to 0. So you turn around and you set this thing equal to 0. 0 is equal to 10 e to the minus 5t times 1 minus 5t. And you solve for t. T turns out to be 1/5 of a second. Okay, I think that's right. That goes away. Yes. Okay, 1/5 of a second. So 1/5 of a second is 0.2 seconds. So we'd have that maximum there. Well, this should be handy too, because I think we're going to need to get that derivative before we're done with it. Well, let's go on and look then at the voltage. We'll come back to this. I guess I didn't do a very good job of saying what we were trying to find. Much of this is really just going through what we were given. What we'd like to find is the expressions for voltage, for power, and for energy, and we'd like to plot those. Okay, so very similar to what we did with the capacitor. So what do we have for our governing equation for the voltage? We know that the voltage is equal to L times di dt, right? So what was the value for the inductance? That was that 100 millihenries. So I have 100 times 10 to the minus 3. That's what? 0.1 then. And then I have to multiply this by di dt. Well, we've got di dt. It's right there. So we'll come back and use this. Like I said, this was kind of an interesting side, but the important part was actually to do that because we're going to use that. So I multiply this by 10 e to the minus 5t times the quantity 1 minus 5t, which gives me what? Gives me e, because the 10 cancels with the 0.1, e to the minus 5t times 1 minus 5t. Let me double check that. Yeah, that's volts. This is for t greater than 0. I haven't said much about t less than 0 is 0, so the voltage would also be 0. So let's see what that looks like when we plot it. So t in seconds and our voltage here in volts. We would have 0 up to 0, and then all of a sudden, if you put 1 in here, you're going to have what? It's going to come up to a value of 1.0, and at cross the axes here, and do something like that, where this point here, where it crosses, is 0.2. Which is kind of interesting. Do we have maximum voltage where we have maximum current? I mean, our current graph looked like this, right? We get our maximum current at 0.2. This was, let's see, did I give you the units for the current? We'll just take this as amps. So amps. So we get our maximum current at 0.2, but we don't get our maximum voltage. That's okay, because no one ever said that voltage was proportional to current. Rather, voltage is proportional to di dt. So that's the symbol for proportional. So voltage is not proportional to current, so that's why we don't see this being a maximum where we have a maximum current. Rather, it's proportional to the derivative of the current, and that's why we get that value going through there, where the derivative is equal to 0. That's going to go to 0. So it is working out physically, and it's also working out from a math standpoint. Now, what do we learn about the capacitor? We couldn't have an instantaneous change in terminal voltage, right? Would this be an acceptable graph for the capacitor? No. What if I'd mislabeled these? What if I was trying to sell you this graph here for the inductor as current? Well, we know that the current in an inductor can't have an instantaneous change. Does the current have any instantaneous changes? No. Could we tolerate this discontinuity here if this was a current graph? No, we could not. So I'm glad this is the voltage graph. I'm glad it's an inductor because it's behaving like it should. So I just wanted to look at a couple of those things. Well, let's continue on with power then. And we could say that power is equal to, what do we have? L times di dt times I, or I of t. So we can say that this is what? 0.1. Or actually, I've got dl dt already, don't I? I could just say it was this thing, couldn't I? So let me do that. E to the minus 5t times 1 minus 5t. And then I'm going to multiply this by I, which we said was 10t e to the minus 5t. So when you go through there, this turns out to be 10 t e, going to add exponent, so it becomes minus 10t times the quantity 1 minus 5t. This is watts. So that's the expression for the power. So if I graph this, t in seconds, and we've got p of t, power, in watts. It's going to look something like this. It's going to be 0, and it's going to come spike way up and down and do something like that. Okay. where this is probably, this is going to be, I mean, if we were to say watts, and say this 0.1, 0.2, it goes above 0.2. The important point to notice is where it crosses here. Where do you think that is? Yeah, 0.2 seconds. 0.2 seconds where it crosses. So here we have energy and power going in, and here we have power going out. Okay, and we'll come back and look at that in a bit more detail in a moment, just like we did with the capacitor. So we've got volts, we've got power. Let's finish up with energy. So with energy, we said that for the inductor we had 1/2 L I of t squared. Okay, so we would have 1/2 times L, which is 0.1. That's 100 millihenries. And then what do I have? I squared. So I was, do we have a value for I? Well, there's I right there, isn't it? So 10t e to the minus 5t. How do I square that thing? Well, it's going to be 10 squared t squared e to the minus 5t. So I'm going to be minus 10t, right? Okay, so when I square that thing, so I can say then when the smoke clears on this, I should have, let's see, 100 times 1/2 is 50 times 0.1 is 5. T squared e to the minus 10t, right? So when I graph this, I'll say that I have t in seconds and energy, and I'm going to put this in millijoules. So we should have, did I get the last one right? I think I put the last one in watts, and yeah, I changed my values. Good. Yeah, we've got kind of small numbers for this, so I'm going to go ahead and use millijoules. So it's 0 up to here, and then it comes up to some maximum value, drops down, looks a lot like the current expression, which it probably should, shouldn't it? And where's this maximum point? Turns out to be 27.1 millijoules, and at that point you could imagine that is at 0.2. So what I'd like to do is I would like to integrate the power, just like what we did with the capacitor. I'd like to integrate the power. So our last thing, we've satisfied the problem. The problem asked us to come up with the graph and the expressions for the voltage and for the current and for the power and for the energy, and we've done that. But I'd like to take it one step further, and I'd like to then find the integral from 0 to 0.2 of p of t dt. And then I'd also like to find the integral and ask the question if it's equal, the integral from 0, or not 0, but 0.2 to infinity of p of t dt. Okay, so we'll see if we can do that. Essentially, that is to ask the question, the area under here versus the area under there. So when I go through that, I'm going to be evaluating a couple of integrals. I'm going to be evaluating the integral from 0 to 0.2 of p of t, which is going to be what, 10 times, let's see, p of t, make sure I get this right, 10t, yeah, I think I'll multiply this out, so I'm going to have 10 times, I'll say, is that going to work? Yeah, I can just leave it like that. I won't clutter this up. We'll talk a little bit. I used to in the past get a little better form to integrate. Probably going to use a computer algebra system anyway. So let's at least get it started here. So I've got then, I'm just using this one, 10t e to the minus 10t times the quantity 1 minus 5t dt. So I'd want to find that, and I'd also want to integrate from 0.2 to infinity, okay, of the exact same thing, 10t e to the minus 10t times 1 minus 5t dt. Those are actually not very easy integrals to do. If you go through them, you're going to end up with this one, 0 to 0.2, as equal to 27.07 millijoules. And if you go through this one, it's equal to minus 27.07 millijoules. And the way that you the way I actually did that, and I'm not going to go through it too much, I used the form that looked like this, the integral. So you might look at forms in a calculus book, or if you know, there's nothing wrong with a computer algebra system, but if you want to do it by hand, you don't want to spend a lot of time with integration by parts and whatnot. I would go look up a form in the Chemical Rubber Company's CRC Handbook of Chemistry and Physics, or the CRC Math Handbook has the same tables, or even a good math book will have the tables. And you, of course, do a Google search and it usually pops right up, integral forms. But if I integrate x e to the ax dx, that's one that I need, because that's going to turn out to be equal to e to the ax divided by a squared, and that's ax minus 1. And then I'm going to have a bit more of a problem here, because that's going to work okay for this one, where I've multiplied this 10t times the 1. When I multiply the 10t e to the minus 10t times the minus 5t, I have t squared, and I don't have an x squared, so I'm going to have more troubles. So I'll have to use the form that the integral of x to the m e to the ax dx is equal to x to the m e to the ax divided by a minus m over a times the integral of x times the integral of x to the m minus 1. So in our case here, m was what, 2, so m minus 1 gets us back to this one. So you'll end up actually having to use this one twice. So I have x m minus 1 e to the ax dx. Okay, so those are the two forms that you would do. And what I got sidetracked here, I was trying to rearrange this so it fit better into these forms. I don't know whether that's important anymore. A lot of people just turn to a computer algebra system, and that's fine. What's interesting is what comes out of this thing. We see that this is a positive. So we have a positive area here. That's essentially the area under there. And we have a negative, which is a negative area there. It also shouldn't get past us that this 27 millijoules is that number there. So just like with the capacitor, with the inductor, what's going in terms of power has to equal what's going out in terms of power. Now, there's internal losses. Remember, we were thinking of the inductor like this. In real life, that inductor has a lot of resistance to go along with it, and so that'll be something that we don't want to forget about. Well, when we get together next time, we let's see, make sure I've wrapped this up. This is yeah, this is what's going in. This is what's going out. I think I mentioned that already. I think I'm good. When we finish up next time, or when we continue next time, we're going to talk about how do we deal with inductors that are in series arrangements, how do we deal with inductors that are in parallel arrangement, and then before we leave this section on energy storage elements and inductors and capacitors in general, we're going to take and put a capacitor, not an inductor, but a capacitor back into an op-amp and hopefully come up with some interesting things. So that will keep us busy next time. Thank you for watching and take care till then.